What's up, everybody? Today we are going to talk about something called Bézout Matrix. Okay, and we are going to learn this, right? And then what we have learned at the end of this, like, I guess, tutorial video, then we will apply, right, the infos here to the another subject, which is called Hermite-Fujiwara matrix. Okay, and again, it will take us for for like 10 minutes or so. Okay, and then by using one and two, by using those two topics, okay, we are going to talk about static output feedback array type control subject. Okay, which is of course what our goal is. Okay, but to be able to talk about this subject, right, sorry, to be able to talk about this subject, first we need to get this Bézout matrix and also Hermite-Fujiwara matrix out of the way, right? And these are just some type of formulas, right? I mean, you don't need to learn new, like conceptually new things, right? Okay, and right, Bézout matrix, right? In a nutshell, is this: you have two polynomials, right? And I call it here f of x and g of x. You have basically two polynomials. For example, these are examples, right? By the way, I get those examples, right, from Wikipedia page. If you type Bézout matrix like this, okay, at wikipedia.com, right, and this is the example they introduce here. Okay, all right, Bézout matrix. You have two polynomials, right? This is some type of machinery or some type of formula that we are going to talk about now. And you are going to give me two polynomials, and then this machinery will give us some matrix, right? Some mean, for example, we have, this is third order polynomial, right? Okay, and this is second order, right? I mean, there is a formula, right? Maximum of degree of f and degree of g, okay, and okay, this n is this. So what is the degree of f, which is 3, and what's the degree of g polynomial? 2. All right, the maximum of is 3, right? Okay, and then basically, and since we have 3, we will have like n plus 1 by n plus 1 matrix. Okay, and so again we have two polynomials, okay, and then Bézout matrix corresponding to those two polynomials is a matrix, right, populated by just constant numbers, okay, just constant numbers, nothing like x or y, it doesn't have that. All right, let's say it's like 1, 2, and it has to be symmetric, by the way. Okay, so let's something like this. Okay, right, not for this problem, but something like this, a matrix n by 1 plus n by, I'm sorry, n plus 1 by n plus 1 matrix. Okay, all right, this is right in a nutshell introduction. All right, maybe it would be better if I just got rid of all those. All right, okay, this was the general formula. All right, okay, how we are going to do this? We are going to do this by using this easy formula, right? And this part is, I mean, you get what it is, right? And then the laborious part will be to determine these b sub ij are in common coefficients, basically coefficient numbers. All right, and I mean, let me tell you something. Just one word, okay? MATLAB. MATLAB is going to do that. MATLAB doesn't have a built-in like Bézout Matrix or something command, but by using symbolic toolbox MATLAB functionalities, right? I mean, it is something that we can, program ourselves for our specific problem, right? And it will be really easy, right? Okay. For example, even this formula, you can consider or you can imagine how annoying it might get, right? Okay. For example, I mean, these are like simple polynomials, but right, you can of course imagine, larger polynomials, right? Okay. So this is the formula, but now we are going to look at one particular example, and this will get, drive the point home. And okay, this is the formula, and so let me call it example. Okay, we have f of x and g of x. Okay, let's use this formula, right? And what we have is this. I'm going to type it. If you use this formula, right, what you get is 15 x squared y squared plus 3 x squared plus 8 xy plus 3 y squared minus 1. Okay, this is it, right? This is it. Okay, so now what is this expression, you might ask yourself, maybe. All right, when you have this, I would, advise you to have, as soon as you have this expression, okay, I would advise you to draw some type of table, and I equals 0, I equals 1, I equals 2, I equals 3. Okay, because remember our n is 3, right? Start from 0, 1, 2, n, right? N, our n number, right? And these are, again, right, these are rows. Okay, these will be the like row indices of our, prospective matrix. All right, and all right, these are row indices. Okay, and let's do the same for our column indices. And j start from 0, of course, right? J equals 0, j equals 1, j equals 2, j equals 3. All right, and then you will have like 16 terms, right? Here you have those 16 terms, and by the way, this will be symmetric matrix. Okay, so you don't have to fill all of the 16 terms, right? And okay, so here, for example, and let's also keep this in mind, right? And here in this location, you are going to type, right? You are going to write down, for example, I equals 0, j equals 0, right? Okay, here again, look at this, right? X I X, sorry, Y to j, right? Okay, so what is this for this point? This is x to 0, y to 0, right? Okay, so I mean, this basically means 1, right? Okay, so meaning constant number in our expression. Okay, what is this? Of course, minus 1. All right, so let's type minus 1 here. Okay, all right, so here, what is the, I guess, term that we need to look at? X to the 0, y to the 1, right? Okay, so question, what is the coefficient of this x of this term? All right, this is our expression. Okay, this is our term. Okay, what is our coefficient of this term? Let's look at this, and it is 0 because we don't have 2x, or I'm sorry, wait a sec, 0, right? Okay, you know what, I think I should do something like this. Wait a sec. All right, let me copy this expression and paste it right over here. Okay, and then I'm going to do something that will make things easier. Okay, all right, and right, it's gonna take some time, not gonna lie, but just to get the general idea, I think it will be necessary. I hope I don't make any mistakes. All right, first mistake. All right, later I will check it, by the way. 3 y2 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 1 2 3 y3 y3 y3. Let me check this. This is, I use this of fish. This is correct. This is correct. 0 2 0 3 1 0 1 1 1 2 1 3, right? Okay. Okay. 2 0 2 1 2 1 2 2 3 3 0 3 1 3 2 3 3. Okay. All right. Question. What's the coefficient of this term? Just look at this term expression and answer is -1. Okay, great. Question. What is the coefficient of this term? Look at this expression and answer, please. Pause and answer, please. All right. And it is 0, right? Because we don't have any y term in our expression. All right. Question. What is the coefficient? What's the coefficient of this term? And y squared, right? Yeah, we have this, right? 3. All right, great. Question. What's the coefficient of this term? Look at this and answer. It's 0 because we don't have any y cube term, right? Okay. Question. What is the coefficient? It is, I'm looking at this when we don't have any x term, so it's 0. By the way, this must be like symmetric. We talk about this, right? Okay, so for these circumstances, right, I would advise you to fill in all those entries and then look at if it is like symmetric, and then maybe you can some type of like error correction mechanism, right, built into your process. All right, so 0, right? Okay, so xy, yeah, we have this, right? It's 8. Okay, xy squared, no, we don't have this. Xy cube, no, we don't have this. Actually, you know what, we don't have any y cube, so those terms we can just directly fill them as like zeros, right? Okay, and I am looking at this expression, and we don't have any x cube terms, so we can also just directly fill in those zeros. All right, so where we were, yeah, x y squared, right? And again, it's 0, right? We don't have that term. X squared, yeah, we have here 3. And by the way, again, it's like symmetric. Okay, here, great. And x squared y, again 0, and again it's like symmetric. Great. And look at this, x squared y squared, and yes, here 15. All right, so this is our this is our Bézout matrix. Okay. Okay. So, and maybe we should go back to MATLAB and try to see how MATLAB would, you know, construct that Bézout matrix for our purposes. All right. First of course, you need to, initiate your symbolic variables x and y, because we had x and y, right? Symbolic indeterminates. All right. This is our f of x, okay, and this is our g of x, right? Remember, two polynomials, f of x and g of x. All right. And then because of let's go back to tablets and remember what the formula was. Okay, yeah, this is our here. This is our formula, right? So we have f of x and we have g of x, right? What we need to construct is, first g of y, right? And then f of y. So let's construct them. All right. We have f of x and we have g of x, and then we need to construct f of y, and g of y. All right. It's easy, right? You can use just substitute command, substitute, right? And here we have substitute y for x. Okay. Let's run it. Okay, this is our f of x. Let's substitute and construct f of y here. This is f of y, and you can just check it. These are like same expressions, right? Just another different indeterminates. All right. G of x, here, g of x. I feel like you're able to see the screen clearly. All right. Okay, and then again the same thing for to construct g of y here, g of y. All right. Again, this is our formula, right? Okay, f of x times g of y minus f of y times g of x divided by this term, which is x minus y. All right. Here, just use it, and here you can see. By the way, this is the formula, right? And when you have that formula, you need to be able to simplify that expression so that what you have is polynomial, not rational expression, mind you, right? Just the polynomial, right? And this is not polynomial, this is rational. So we should be able to simplify this, and conveniently we have simplified function. Okay, and what we have is a polynomial in x and y. All right, but this is a polynomial, right? Okay, this is critical. If you have that something like this, you should, check your previous comments lines, right? That would indicate you have made some, or you might have made some mistakes or something. Okay, so now by using this, I guess, to variable polynomial, right? You need to construct that Bézout matrix. Okay, so first of all, since we need to construct our n plus 1 by n plus 1 matrix, right? Let's use that line. First of all, let's determine what n is. 3. Okay, this is the formula. We have talked about this, right? Okay, let's get back to the tablets. Okay, here, this is the formula, right? Okay, we just used. All right, and then Bézout matrix. Okay, let's use that. Okay, and before running this for nested for loop, right? And we should just talk about this function, right? Constant function. And okay, so it might look messed first, right? But it is not actually. So I'm going to tell you what this function does. the name of it get coefficient coef, right? I mean, you can kind of imagine it means get the coefficient, right, of some term, right? Okay, and you have, first of all, let me change the name. You know what? I'm going to call it expression 1, right? I don't want to just directly say expression, right? And then here I'm going to call it term 1, right? Okay, that's great. So you have some type of expression, and this is, let me show you, this is our expression, okay? And you have some type of term, right? For example, y square is your term, okay? You have expression and you have some term that you want to get the coefficient of, okay? This is important, and this function basically does that. But of course, for any two variable polynomial, and those variables defined as x and y, not a and b, right? Otherwise they will throw an error. Okay, so okay, I don't think I need to answer that, and I am sure if you are familiar with MATLAB, right, you would, you know, leave a comment and say, hey, I mean, that was totally unnecessary. MATLAB has a built-in function or something. I imagine that is something, right? Okay, all right, so you have some expression and you also type term and it will give you the coefficient. Okay, so for example, we call our expression term, okay, inconveniently enough. Okay, let's run it. Okay, this is our expression and we want to get the coefficient of x times y. Okay, x times y is 8, right? So if this function is working properly, it should give us 8, right? Oh, that was okay, wait a sec. I need to run it as a section. Okay, otherwise it won't, you know, consider this function. Okay, and the answer is 8, right? Okay, so let's try to get the coefficient of this term. What is that? Let's look at this expression. X squared times y. Do we have x squared times y squared? We have x squared. We have x times y. We have y squared. But we don't have any x squared y, right? So it should, what we should get is 0, right? Okay, let's run it as a section. And the answer is 0. Okay, that's great. So, you know, you kind of get the feeling that at least it's working properly, right? Okay, so this is the function we use, right? Okay, so just run it now. Okay, before running that, just let me explain the idea, right? First of all, you have two for loops, right? It's obvious that we are just, you know, iterating over the entries of this matrix, right? Just when I equals 1, and then you get j equals 1, and then j equals 2, and then j equals 0, j equals 1, j equals 2, and j equals 3. Okay, that's great, right? Okay, and since, you know, MATLAB doesn't like x of 0, right? The zeroth index of a vector doesn't like that, right? And we need to, you know, subtract 1, all right? And you construct the term, and then again simplify, right? And then get the coefficient of that term, and then write it into our Bézout matrix, okay, variable. All right, so let's run it again. Okay, this is basically the answer. Okay, and if you check the Wikipedia page, this is what you need, you know, this is the example they show you, right? Okay, and again, it might sound like what's the purpose, right? But in the next video, we are going to talk about something called Hermite Fujiwara matrix. Okay, and this, and then that subject is the subject that we are going to be focusing on, because we are going to use that matrix, right, to, let me just give a little summary, to construct, right, to construct some type of constraints to formulate our static output static output feedback LTI problem, control problem. Okay, all right, and it will not be an LMI, right, linear matrix inequality type of problem like convex problem. It will be a BMI, like not linear but bilinear matrix inequality, and means it will not be a convex, right, function. Okay, and all right, I hope I don't forget to put this, like it is like 40 or something lines of code, right? And okay, I am going to upload this code, and you can access to this code by using the GitHub page link. The link I will put it in the down in the description. So thanks for watching. Okay, see you next time.